All right, hopefully y'all can hear me. I'm going to go through the exam quickly and hopefully that'll be helpful for some people here. Should be able to see the exam here. So first question, the equivalence point and the endpoint in a titration are the same thing. No, they are not. The equivalence point is when we're at the exact same stoichiometric ratio of the two different things, whereas the endpoint is typically somewhere after that when now we've actually seen some response from our indicator. Question 2, we have titration. What volume of 0.125 molar sulfuric acid would be required to titrate 105 milliliters of 0.1 molar ammonia to the equivalence point? So there we go, whiteboard loaded. So the big thing here is that, there we go. Yeah. Okay, there's our H2SO4. No, I don't like that. There we go. All right. Here's our H2SO4. And that's our acid and our ammonia. The NH3 is our base. When they react, each one of those H pluses is from the sulfuric acid is going to protonate our ammonia and give us NH4 plus. We technically have two acidic protons on the sulfuric acid, so it's actually going to be able to protonate two of these, giving us two of those, and then our conjugate base from the sulfuric acid, which is just the sulfate SO4 minus. So the important thing here is the acid and the base react in a 1-to-2 ratio. So we can take a volume of our base, 0.105 liters, 105 milliliters, multiplied by its molarity. And we can see that we have 0.0105 moles of NH3. But what we need is not that same number of moles of sulfuric acid, but half as many based on that stoichiometric ratio. So we need 0.00525 moles of H2SO4. And if we divide by the molarity, we get 0.42 liters or 42 milliliters. All right, KSP for calcium fluoride. So we're looking for this. We know that the molar solubility or the concentration of this in a saturated solution would be 2 times 10 to the negative 4 molar. So when calcium fluoride dissolves, we get calcium 2 plus ions, and we get 2 fluoride anions. So what this tells us is for every calcium fluoride that goes into solution, we get 2 fluoride. So we have a 1-to-2 relationship there. And for every calcium fluoride that goes into solution, we have 1 calcium. So the molar solubility tells us we can dissolve 2 times 10 to the negative 4 moles of calcium fluoride. That should be then the exact same concentration of the calcium because it's in a 1-to-1 ratio. So normally, we'd write out our ice table. We have 0 of these. We're going to form X of these and 2X of these. So at equilibrium, we'd have X and 2X. And our equilibrium expression would look like that. And what we put in here would be X, 2X squared. So at the end, we'd have 4x cubed, but we don't have to put x in there. We can actually go in and say, hey, because of the molar solubility, I actually know exactly how many calcium ions I'm going to have. And how many fluoride. So now I can put that in 2 times 10 to the negative 4 times 4 times 10 to the negative 4 squared. And plugging all that in, get to my 3.3 times 10 to the negative 11, which will be my KSP. Which of the following would reduce the solubility of barium iodide? So there's my barium iodate, and as that dissolves, we get barium 2 plus ions, and we get 2 of these. These are aqueous. So with those different salts, what we're looking for is the common ion effect. So I'm looking for a salt that has an ion in this, and the only one of these would be the K, or the potassium iodate, because when that dissolves, we get these 2 ions, and there's my ion in common. So that would reduce the solubility of that salt. Sodium hypochlorite dissolves, so we've got the hypochlorous acid, and we've got sodium hypochlorite. So that gives us, when that dissolves, the OCl minus. So there's my weak acid and its conjugate base. So we have a the pH for a buffer is always pKa plus log of the base over the acid. We know that our pH is 7.8. We know our pKa is 7.53. So that means this term right here must be 0.27. So I need to figure out what ratio of base to acid gives me 0.27. So if I take the anti-log of that, I get 1.86. So that means I have to have 1.86 times as much base as acid. I have to have a positive, or sorry, not a, yeah, positive number here, or something, sorry, not a positive, but something greater than 1 to give me that, when I take the log of it, give me that positive value of 0.27. So you could rule out actually right off the bat B and D, because that gives you something less than 1. And only possibilities being A and C. But again, if you solve for the anti-log of that, you'll get that 1.86 to the 1. What's the pH of titration of a strong base with a weak acid? So strong base with a weak acid is going to give us just the conjugate base of that weak acid. So that's why that should be slightly basic. Hydrocarbon contains only carbon and hydrogen. So we have some ratio of carbon to hydrogen, CXHY. We do CO2, and that gives us 12.574 grams. So what I want to do is from the CO2, that's the only place that the carbon can come from. So I want to find out how many moles of CO2 I have, and then I can figure out how many moles of carbon I have. So that should be 44.01 grams per mole. So if I take the 12.574 divided by that, I see that that is 0.2857 moles of CO2. And for every one CO2, I only have one carbon, so it's the same number of moles of carbon. Then we go in and we do the water. We have 6.434 grams of water. So divide that by its molar mass. That will give us moles of water. And then multiply by 2 because there are 2 hydrogens for every 1 water. And from this we get 0.7143 moles of hydrogen. So we know the molar ratio. The only issue here is it isn't, in nice, clean whole numbers. So I probably want to get it to there. So I'm going to divide both by the smallest, the 0.2857. That should give me C1. And H 2.5, 2.5, that's the same as 5 halves. If I want to get rid of a half, I multiply the whole thing through by 2. So that gets me C2, H5. Answer B. A molecule that can both donate and accept a proton is said to be amphoteric. So that could be, something like water or carbonic acid after the first protonation. So it can either accept or donate a proton that's amphiprotic. All right. Titrating oxine, what would the pH be at the first equivalence point? So we have oxine. We don't know what that is, but we are told that we're titrating it with a base, with NaOH. So it must be an acid, and we're also given a Ka1 and a Ka2. So that would also confirm that it is an acid. And it further tells us that if it has 2 Kas, it must be a diprotic acid. So at the first equivalence point, we have lost the first proton, but none of the second. We've created again an amphiprotic species, and the pH at that point is 1/2 the pKa1 plus the pKa2. So I'm just going to take the negative log of each of these to find what is that pKa1 and what is that pKa2. So this is 4.94. And this is 9.82. So we do 1/2 of that plus that. And we get 7.38. Answer D. A hygroscopic substance is one that picks up, so hygroscopic related to water, and it really likes water. So what it does is it picks up water from the air. So alcohol, ethanol is a really good example of this. If you buy Everclear or pure alcohol, the reality is the instant you open that, it is no longer 100% alcohol because it is going to immediately start absorbing water from the air and, essentially contaminating it, reducing it, going from 100% purity to something like, 94% purity or whatever it happens to be. All right, so now we're complexing nickel with DMG. So we're making this nickel DMG complex, and one of the important parts here is that this complex is with DMG in a 1:2 ratio. So we're going to get the formula essentially like this. We have this brass. It contains multiple different types of metals. What we do is we want just the nickel to come out. So we dissolve the brass and we complex the nickel with the DMG. So we're told that we get 0.1 4.23 grams of that nickel DMG complex. Now, we want to know then in the original 0.6 gram sample, what amount of that was nickel. So I need to find out of that 0.1423 grams, how much of that is nickel, and then divide by the 0.6 grams. So I want to know essentially the gravimetric factor, or what percentage, what is the mass to mass ratio of nickel in the nickel DMG. So I can find the mass of the whole thing because we're told the mass of nickel and we're told the mass of DMG, but we don't have just a single one or a single DMG, we have two. So I want to add that in twice. And its entire mass should be 290.93. Take the nickel, the part of interest. There's one in each of these complexes divided by the mass of the whole complex. And we can see that this is approximately 20.17% nickel. So I can take that gravimetric factor, multiply it by the mass of precipitate we produced, gives me 0.0287 grams of nickel. And then we can put just the nickel weight over the weight of the entire sample, the 0.6 grams, gets us 0.0478, multiply 1 and 100, and we get to 4.78%. Answer C. Compound structure with both positive and negative sites is known as a Zwitter ion. So that was in the slides. A lot of the amino acids that we show have the ability to get, partially protonated or to pick up, have a portion of the amino acid that has a positive charge and a negative charge at certain pHs anyway. So a lot of those are examples of Zwitter ions. What's the P? CO2, so essentially the negative log of the cobalt concentration when we carry out this titration with EDTA. So what we're going to have is cobalt 2 plus our deprotonated EDTA, forming that cobalt EDTA complex in a 1-to-1 ratio. We need to figure out how many moles of this cobalt EDTA complex we'd make. So we have 50 milliliters of this 0.1 molar cobalt solution. When I carry that out, I can see that I would have 0.005 moles of cobalt that we're going to potentially complex, or at the equivalence point should more or less be complex. The concentration of the EDTA is the same. It's 0.1 molar. So since they react in a 1-to-1 ratio, that should mean I need the same volume of EDTA, 50 milliliters. So now I know how many moles of cobalt we had, and I know its total volume, 50 milliliters plus 50 milliliters, which is 0.1 liters. So when I carry that out, I can see that the amount of this complex I should have is 0.05 molar. We have 0 of each of these. I'm going to form X of this and form X of that and lose X of this. So we're going to have X, X, and 0.05 minus X. We are given our K, which is 2.818 times 10 to the 16, but but the not all of our EDTA is in that deprotonated Y4 minus form, so I have to go, I have to look at the pH. In this case, it said we were at a pH of 10. I go to the table and at a pH of 10, our alpha, or the fraction of this that is in that form is 0.3. So when I multiply 2.818 to the 16th by 0.3, I get 8.44 times 10 to the 15. So what we've got is 0.05 minus x over x squared equals 8.454 times 10 to the 15. I can rewrite that, isolating that x squared term. My value there that I'm dividing by is very, very large, so I'm going to throw x out. So if I take 0.05 divided by 8.454 to the 15th, I get 5.914 times 10 to the negative 18 equals x squared. And I take the square root of each side, gets me 2.43 times 10 to the negative 9. And if I do the negative log of that, I get 8.61. Which of the following would describe a multidentate ligand? So a ligand is a negatively charged, here, cyanide is a good example of a ligand. It binds at one point. So this is a monodentate ligand. So if whatever we had, I don't know, lead, we'll say, I would potentially be able to complex cyanide with lead. So all ligands are also, are all ligands and all chelating agents are Lewis bases, because, or even with EDTA, you know that we want this to be in the deprotonated form. So it's got those unpaired electrons that it's ready to donate to something. So they're all Lewis bases. And then more specifically, like cyanide here is a ligand, but it's monodentate. It's only going to have one pair of electrons that it can donate. It's only going to bind to that metal at one site, whereas a multidentate, like EDTA, has multiple sites that it can bind to, and that is what we call a chelating agent, a very specific type of ligand. So all the multidentate ligands should also be referred to as chelates and should also be Lewis bases. What type of compound protects some components of a mixture from reacting with EDTA? That would be a masking agent. So if we have multiple metals, we can bring in a masking agent that's going to potentially interact with or bind or prevent some of those metals from interacting with the EDTA, and only allowing us to get, the selective ones that aren't being masked to bind or interact with that. What's the pH of the second half equivalence point when titrating a dibasic compound? So we have a dibasic compound, so that means our pKa, or no, sorry, our pKb one is going to be, there's 4, and our pKb2 is 8. Remember, so that means with this base, it's going to essentially dibasic. So the first base interaction is going to produce or have a pKb of 4. That means the corresponding pKa2 for this should be 8, and the corresponding pKa1 for this should be 6. So if we're at the second half equivalence point, so we start basic and we hit an equivalence point and we hit the second one, here's our first equivalence point, here's our second. We're at the half equivalence point to the second one right here, which in this case, we would have a buffer and it would be equal to pKa plus the log, but this is going to be the log of 1, which is 0. So we're just concerned with the pKa, but in this case, the pKa 1. So that should be a pH of 6. So then we have this figure here. Come on. There. So here's the volume of titrant added. Here's our pH. And we start at a low pH, we go up, and we plateau, and then we go up again, and then we plateau. So what this tells us is because it's a low pH, we're titrating an acid with a base, because we start at a low pH and it increases. And with the volume added, or what we see here is that we don't have just one equivalence point, but we have two. So that means this has to be a diprotic acid. So we could say it's an acid being titrated with a base. So it's A, and it's a diprotic acid, not monoprotic. So also C. So yeah. So then how much HCl would you add to buffer to go beyond the buffer capacity? Okay, so we have equal amounts of acetic acid and acetate, and we're adding HCl. So out of these two things, in the buffer, the weak acid and the conjugate base, the part that this HCl is going to interact with or be neutralized by is the acetate. So we could tell that we have 0.1 liter times 0.5 moles. I have 0.05 moles of base in this case. And we'd have, X amount. It's going to interact with that. And we're going to lose base and produce more of the weak acid. The buffer capacity is essentially, or the range is the pKa plus or minus 1. We know in this case we're adding acid, so we're going to become more acidic. So we're looking at the pKa minus 1, and we want to know essentially when are we going to get there. So for this to be -1, that'd be the pKa plus the log of the base over the acid. For us to get to a -1, that would mean we'd have 10 times as much acid as base. So we're looking at a 1:10 ratio, or 0.1, and that's going to be equal to 0.05 minus X, because we're losing base, and then 0.05 plus X on the bottom because we're creating that much acid. So if I multiply both sides by multiply by 0.05 plus X, then we get 0.005 plus 0.1 X equals 0.05 minus X. I'm going to add X to both sides and subtract 0.05 from both sides. So I get yeah, 0.045. So I get 1.1x equals 0.045. Divide by 1.1. And you get about 0.0409 for the moles of acid. Now it's 1 molar, so the volume will essentially directly correspond to that. We'd multiply that by 1 to go to liters, or we'd have 0.0409 liters, or 40.9 milliliters. So I could add 40.9 milliliters of the HCl and be right at the end of the buffer capacity. And as soon as I add any more than 40.9 milliliters of HCl, we'll now be beyond the buffer capacity. The only value of choice that's above 40.9 is the 41. 19, which of the following is a good analysis method to determine the amount of protein? That was the Kel-Gel analysis because it analyzes for nitrogen. All of our amino acids or proteins contain nitrogen. So if we can essentially know that the only nitrogen containing species is a protein in there, or isolate the protein from it, then once we can do the Kel-Gel analysis, find out the amount of nitrogen, get that to correspond to the amount of protein, and we're all good. Whereas EDTA is more specific for metal complexes, and genetic sequencing is going to, be more interested in the specific DNA. Are we looking for, cysteine or guanine, adenine, etc. And then predict the acidity, basicity if we dissolve NH3 or ammonium nitrate in water. So if I dissolve this in water, we're going to get 2 ions. I'm going to get ammonia, and I'm going to get nitrate. There we go. This is our cation is always our base. In this case, this is the conjugate base of, remove the hydrogen, we get ammonia. A weak base, meaning that this is, or sorry, not conjugate base, but conjugate acid. There we go. This is the conjugate acid. Our cation is always our acid. Conjugate acid of a weak base. The anion is the conjugate base. In this case, we add hydrogen to it. We get nitric acid, which is a strong acid. So that would mean that this is a negative base, and this conjugate acid is a weak acid. So we would have a slightly acidic solution in this instance. Okay, that's everything. Hopefully this was helpful. If you think of any additional questions, let me know. If something seems off and you want to check the Scantron, stop by any of my office hours by all means. Hopefully this helped if you weren't 100% sure about why an answer was what it was. And I'll see you Monday the 23rd.